Hello everyone, my name is Nachiketa. Welcome to the presentation titled DC Link Voltage Feed Forward Controller for Buck Active Power Decoupling Circuit. This is the presentation outline. Here we have a generic block diagram of a single phase power converter. We have DC source or load, then we have AC single phase source or load, and then we have our single phase power converter. The instantaneous power on the AC side is consisting of a oscillatory component of power oscillating at second harmonic frequency. Hence, to ensure power balance, the single phase power converter must buffer this power. Hence, and ripple energy storage is required. Buck active power decoupling circuit is one such high reliability ripple energy storage element. Let us see the system under study. We have utility grid, then we have a filter inductor LG, an active rectifier, then we have bidirectional buck converter based active power decoupling circuit. Here CBF is the energy buffering capacitor which will buffer the second harmonic component of the instantaneous AC side power. Then we have small capacitor CBus responsible for high frequency filtering. Then we have DC resistive load. Feed forward control is popular to improve the transient performance of the system. For bidirectional buck converter based active power decoupling circuit, load current based feed forward is suggested in the literature. However, in this feed forward, the feed forward signal is processed by a low pass filter or a phase delay block. Hence, in this case, the operation of the feed forward is not up to the mark in presence of rapid load changes. Secondly, a capacitor current based feed forward is also suggested. In this case, the current flowing through this high frequency filtering capacitor is considered for synthesis of feed forward signal. Hence, we need additional sensors. Also, due to high frequency current through this capacitor, it is difficult to accurately estimate or sense the low frequency components of current, and hence this technique is difficult to implement. So what is our motivation? The motivation is to figure out a feed forward controller which does not require additional sensors, and also it is easy to implement. So why we select DC link voltage as a feed forward signal? The DC link voltage of the active rectifier is controlled by three parameters. First one we have is the filtering capacitor CBus which bypasses the high frequency ripple. Secondly, we have buck active power decoupling circuit which bypasses the second harmonic ripple of the instantaneous power. Then we have DC link voltage controller of the active rectifier which bypasses the low frequency ripple corresponding to its bandwidth. Typically, the bandwidth of DC link voltage controller is limited to 10 Hz. So, a step change in load current is understood as in terms of its frequency component. Out of the frequency components of the step change in load current, the second harmonic part will be bypassed by the buck active power decoupling circuit, whereas the low frequency part, less than 10 Hz part, will be bypassed by the DC link voltage controller. However, the remaining part is forced onto the small value of capacitor CBus, and hence during rapid load changes, the DC link voltage fluctuations are fast and large. Hence, the DC link voltage contains the information about energy imbalance in the system and hence ideally suited for a feed forward signal. So this is the fundamental working principle of proposed controller. So here I am explaining the working principle for step decrease in load. However, the exact opposite will happen in case of step increase. So in case of step decrease in load, the DC link voltage swells, which means there is excess energy in DC link. The excess energy must be rapidly transferred to the buffer capacitor to reduce the DC link voltage overshoot. Also, it must be noted that the buffer capacitor is not an energy sink. Hence, the buffer capacitor cannot continuously operate with the absorbed excess energy. Hence, the buffer capacitor must transfer back the excess energy at a controlled slower rate. This low rate ensures that the DC-link voltage controller of the active rectifier mitigates the fluctuations caused due to discharge of the buffer capacitor. This is the fundamental working principle consisting of two key objectives: fast increase in buffer capacitor voltage and slow decrease in buffer capacitor voltage. This is the proposed control technique. Here we have V-bus, that is DC-link voltage, as input to the proposed feed forward, which consists of an array of high pass filter and gain. Sum of all these paths is given as DFF of duty ratio feed forward. In case DC-link voltage quickly rises, we are quickly increasing the duty ratio, increasing the voltage of buffer capacitor. Now we need to find a way to slowly discharge it. Here the average voltage controller comes into play. We are calculating the average voltage across buffer capacitor, comparing it with a reference, and then we have a slow PI controller. So bandwidth of this PI controller is 1 or 2 Hz. Hence this average voltage controller will slowly discharge the buffer capacitor, satisfying our second objective. Apart from these two controllers, we have buffer current controller responsible for inner current loop and ripple voltage controller controlling the steady state ripple in the DC-link voltage. These are the simulation results. Here the parameters of the simulation are given in the paper. When we have step decrease in the load from 310 watt to 10 watt, we see that in V-bus DC-link voltage we have an overshoot of 118 volts. With proposed controller, the said overshoot is reduced to only 47 volts. Also, we see our proposed controller in action. So this VBF is voltage across energy buffering capacitor. So energy buffering capacitor voltage is rapidly increasing first and then slowly decreasing. Okay, and then average is coming back to the same value as it was before the transients. Okay, so this is how the proposed controller is fulfilling both of the objectives I mentioned earlier. So let us see one more phenomenon. Like I said, the proposed controller is consisting of an array of high pass filters. So how many high pass filters should be there? So here I am showing results for 3 high pass filters, 2 high pass filter and only 1 high pass filter. Okay, so here we see that as the number of high pass filters is going on increasing, the DC-link voltage overshoot is reducing. However, the degree of improvement achieved is reducing. So for let us say for this third case where we are going from 2 to 3 high pass filters, we are achieving only 9 volt reduction in DC-link overshoot. Hence, there are diminishing returns in terms of DC-link voltage overshoot reduction as the number of high pass filters goes on increasing. Hence, there is an important design trade-off between complexity of implementation and DC-link voltage overshoot. These are the results for DC-link voltage undershoot mitigation. Without proposed controller, we have a 63 volt undershoot. With proposed controller, we have 41 volts undershoot. Also in this case, we see that the voltage of the buffer capacitor VBF is rapidly reduced first and then slowly increased, which is opposite of what was happening for step decrease in load. So this paper proposes a DC-link voltage feed forward controller. In this paper, DC-link voltage fluctuations during load changes of the active rectifier are reduced. There are no additional sensors required for synthesis of feed forward signal. Also, proposed method supports 2-terminal implementation of the ripple energy storage. In addition to the details presented here, small signal analysis of the controller and guidelines for the parameter selection are presented in the full paper. For 60% step decrease in load power, the proposed controller reduces the voltage overshoot by 60%. For 60% step increase in load power, the proposed controller reduces undershoot by 35%. For additional details, please refer to the paper. Thank you for your time.